Okay, so we've been talking about soil water for the last couple lectures. And if we're going to be talking about soil water, it makes sense for us to start talking about soil air. Okay? We also introduced with soil water this idea of the redox potentials and issues of respiration and the effects of water. Well, let's actually talk about how that directly relates to the air component and redox potential there. All right, so you have seen this slide, parts of this slide for a couple times. But basically, we're talking about the soil system. So we're talking about a three-phase system. We got the solid part, mineral material and organic material. We also have the liquids and the gases. Okay, so we've got the solids down, we've got the liquids down. Let's actually start talking about the gases. Okay, when we talk about soil air, often people just think of the oxygen, but we're really talking about the whole atmospheric system, much like the atmospheric system that we breathe. You know, what is it? Very small percent of it is actually oxygen. Okay, most of it's nitrogen, right? Okay, well, the truth is that's what's going on in the soil atmosphere as well. But in the soil atmosphere, respiration is happening just as it is up here. But in the soil atmosphere, respiration is in a restricted area. It's in a restricted zone. So one would think as things happen in that area, that pores, that the gas composition of the soil air is going to be different than the gas composition of the atmospheric air up here. Does that make sense? Okay. And so if we look at that, obviously things are eating down there, and if they're eating, they're consuming oxygen and they're producing CO2. Because the CO2 is being produced down underneath the soil, for that oxygen to be replaced, the CO2 actually has to come out and the oxygen has to come in. Okay? And that's why you have these gradients. So this is why you have this change in concentration of gases in the soil atmosphere versus up here. Okay? This is just a chart to sort of give you an idea about what that composition looks like. And it's not dramatically different. But it's different enough, just a little bit, it's different enough to actually create some real changes in how the atmosphere is being used. Okay, so here's the gases: nitrogen, oxygen, CO2. Soil air versus the atmosphere. Nitrogen, a little bit less. Okay, there's a little bit more nitrogen in the soil atmosphere. O2, 20% down there, 20.9. But look at the CO2 concentration. Dramatic increase in CO2 down below. Okay, now I think my next slide is a good example. Okay, this is why. Okay, so if this is the soil pore and down here is where all the things are being respiring, okay, for that CO2 to get out and for oxygen to get in, because there's no photosynthesis down here. There's nothing producing oxygen down here. It's all being produced up here. So for that oxygen to get in, the CO2 has to exchange. Okay, and that exchange is really controlled by diffusion. Okay, so air movement within the air is basically controlled by two processes. One is diffusion and one is mass flow. Mass flow is a little bit less important. We'll talk about it for a moment. But diffusion is really what's driving most of this exchange. Okay, the rate of diffusion basically depends on four things. And if I'm going too fast, slow me down. Sorry, it's Friday, I'm on a race. Okay, the first is soil water content. That was our last two lectures, right? How much water is in this volume of pores is going to affect how fast the gas exchanges. Gas exchanges very quickly up here in the air. There's not a lot of molecules in this volume of room. But if I fill this room with water, the gas exchange would slow down. The molecules would move slower. Okay, they would run into things. They'd run into more things and you'd start seeing bouncing around. And that would slow the distance traveled with each tangent. Does that make sense? Okay, so how much water is in the soil is going to affect that exchange rate. The size and the number of the pores. Okay, here it's one large pore. This room is one large pore. But the same volume in soil, lots and lots of pores, small. So the pathways for that exchange are greatly restricted. The continuity of those pores is extremely important. If I have a pore that goes way up here and it stops right here, any kind of gas that's exchanging up in here is just going into a dead end. It has to come back out and find a pore all the way up to the atmosphere, above the air atmosphere. Okay? And then finally, the temperature. Why is temperature important? This is not the C10 rule. Why is temperature important? We're getting into the heating season of the year, right? Or you can think of this in the middle of the summertime. Anybody have a room on the top of the house? It's the hot part of the house, right? What happens to air when it gets hot? It rises. Now, if I have hot air up here and cold air down here, do you think there's a lot of impetus for that hot air to be rising from here? Because the air is up here is already hot. Okay? So that temperature plays a big role in that exchange. Okay? And that's diffusion. Now, we also have mass flow. To a certain extent, it's less important. I mean, there's some events. But we sort of talked about this when we were talking about water, and we were talking about the Artesian effect. When I've got a pressure gradient coming through, that pressure gradient potentially is going to push or pull, if it's a low pressure versus high pressure, it's potentially going to push or pull through these pores. You know, if I have a high pressure up here and a low pressure here, we're going to see sort of a push this way. On the other hand, if I have a low pressure system coming in, weather-wise, we're going to start seeing an exchange coming out. I mean, this is a glorified example of a cave. You know, when you go into caves and there's breezes, that's basically what we're talking about. Okay, cool? All right. All right, so now I said that we're going to be talking about air, but we're going to take a step back and we're actually going to talk about water for a little bit, but we're going to be talking about water in the context of air. Okay? Saturated soils quickly become deficient in O2. Now, O2 is not necessarily air, but it's part of that air, that soil air. The question is why? Why do saturated soils quickly become depleted in O2? What's going on down there?
Gas exchange is slow and the water is displaced.
Okay, so gas exchange is slow and water can potentially replace the oxygen, so oxygen and everything else that's in the soil atmosphere can be pushed out. Okay, so that's one. Okay, that's an exchange where we have an increase in water. Okay, but let's say we have the water there already. Okay, water levels are not changing. We are still going to see a loss of oxygen. Why?
Things are respirating and there's no more oxygen coming into them.
If no more oxygen is exchanging into the system, and things are respiring, they are aerobic aspiration. You know, we're oxygen breathers, okay, versus anaerobic systems. If they're breathing, they're using up the O2. So just by respiration, the O2 levels are going down. And if the system is saturated, let's go back to the argument over here. If the system's saturated, the exchange rates are going to dramatically drop. So as a result, we're going to have this depletion in O2. Okay? Good classic example of this. You've seen these. These are basically, we're looking at thetas here. So this is the fraction of the total soil volume that's occupied by air versus PT, which is the total volume. That's the porosity. That's the pore space. Versus the theta. Theta is how much water is in the system, right? So if you basically look at a theta of 0, the system's totally dry. Maximum exchange. You start getting to a theta where I'm 50% saturated, or 25% theta. The volume has 25% water. Okay? We're dramatically slowing down. I mean, I drew the blue lines in there. I know it's pretty bad. But, you know, the exchange of that oxygen is going to be dramatically reduced. And that's basically that story, why it's being reduced. Okay, not only are the plants respiring, but if that system goes anaerobic, what's going to happen to those organisms? They die. Okay, and if they die, all of a sudden you have more food down there. Okay, you don't have the organisms that are doing the aerobic respiration, but then you start seeing the decomposition by anaerobic processes. And that in turn is going to dramatically change the composition of that soil atmosphere. Does this make sense? Sort of a tiered reaction as the system goes anaerobic. Okay, so this is sort of giving you sort of a fairly good sort of a cartoon of the scenario. Soil surface up there down to 120 centimeters, basically soil depth, okay? And this is basically oxygen. The more that you go that way, the more oxygen's in the system. The two lines represent rain events, or before a rain event and after a rain event. The first line here is before a rain event. The second line here is after a rain event. Well, this goes back to what your comment was. Well, if water is moving into this system, air is going to be driven out. Forget about the respiration. Just look at the mass flow. Before the heavy rain, oxygen content down to 120 centimeters is about 15%. You get farther up and you get closer to the surface and increases dramatically. Okay? After that rain event, the oxygen is just basically driven out. And this has nothing to do with respiration. This is just mass flow. Make sense? So let's take this a little bit differently. Instead of looking at the oxygen content, let's actually look at the CO2 content. Now, why would I look at the CO2 content? The CO2 is a representation of respiration, of aerobic respiration. Okay, if I'm breathing oxygen, I'm going to be respiring CO2. Okay, so if I look at CO2 concentrations, it gives me a measure of how much respiration is going on. If I look at O2, it doesn't actually tell me how much respiration is going on. It just tells me that there's the potential for respiration. Does that make sense? I look at CO2 to tell me that, in fact, respiration is going on. Okay, so let's look at CO2. This is CO2 concentration. The assumption is the more CO2 concentration you have, the more respiration you have. And then this is depth. Okay, so looking at 0 down to 800 centimeters. Okay, so 8 meters down. Okay, now let's look at a seasonal issue here. We're looking at a dry season versus a wet season. Dry season. Lots of pores. They're not packed with water. I should have lots of gas exchange. My CO2 level is down, though. Wet season, CO2 levels go up. What's happening in this scenario? This is not a case of water moving into the system and driving everything out. Because if the water is moving into the system, like this scenario, my CO2 levels would basically do the same thing because CO2 is in the gas, right? Does that make sense? In this scenario, something else is happening. Oops, wrong way. What's happening? System starts getting wet. What am I going to start seeing happen? This is a dry system, no water at all. If I don't have any water at all, I'm not going to have any biological activity. System starts getting wet. I start seeing an increase in biological activity. And so as a result, I see an increase in the concentrations of CO2. Okay, so we have a seasonal issue where we're actually seeing increases in respiration. We have a seasonal event where we see basically mass flow of stuff moving out of the system. Go.
How do you distinguish the increase in CO2 from respiration from an increase in CO2 that might occur from less gas exchange? Like it's building up.
It's building up, right. So the question is, how would I see the difference between respiration CO2 being involved versus just a buildup of CO2 with less exchange? Good question. I mean, my answer to that, and I do not know if this is actually the instrumentation, how we would do this instrumentation-wise, but my answer to that would be, well, if I'm seeing an increase in the relative CO2 concentration, it doesn't matter whether I have less oxygen in the system or less atmosphere in the system or more atmosphere. The relative concentration of CO2 in that total atmosphere represents that respiration. Okay, so if I have a dry soil, and say it's dry and they still are respiring, okay, granted that's probably not going to be the case, I'm going to have a certain fraction of CO2 in that soil. Okay, now if I reduce that because I put more water in, the relative concentrations between O2 and CO2 are still going to be the same. There's just going to be less of both of them. Does that make sense? Does that make sense to everybody? So the question is really, how do I differentiate between what CO2 is being evolved from respiration? Okay, so if I'm looking at an absolute concentration, this is a percent versus an absolute concentration. So if I was saying that, there's X amount of CO2, I would really want to know what that X amount percentage-wise is with all of the soil. Okay, because then that percentage should stay fairly constant with respiration. It doesn't matter how much actually gas I have in that system. Does that make sense to everybody? Questions on that? Go.
If it's if the soil's sealed off by water, then no more O2 can get in. Then the CO2 concentration is going to rise.
Right.
In proportion to the O2.
Correct.
So,
And that's sort of that measure of CO2, though. But if it does rise, it's telling me that there's respiration.
right, but if the same soil is not sealed off by water and it's getting in oxygen, wouldn't the CO2 concentration be different, even though there'd be the same amounts of respiration?
Okay, so we take a system where it's not sealed off, and we look at CO2 evolution. And then we seal off this, and so the relative concentration of CO2 should increase relative to everything else.
Right.
Okay, but yes, and so I've got a measure of 2 times. Now, how do I compare those 2 systems to each other? I basically look at the total amount. So I got a system that's got some sort of seal at the top. Okay, so no exchange is happening. Now, the reality, that's not going to be the case, but there's going to be slower exchange, but at least with Earth systems, versus a system where there's no barrier. Okay, so you should see a percentage of this being CO2 versus O2, and that's your percentage. Okay, in this scenario with respiration, this CO2 percentage should increase to oxygen because there's no oxygen coming into the system, but there's a buildup of CO2. So how would I tell the difference of respiration in these 2 scenarios? Well, in this scenario, I tell the difference in respiration because I've got this fraction up here. I've got a CO2 O2 fraction up here. Okay. In this scenario, I basically base it on what's happening in a time. I look at it as in a temporal scale, or what's happening over time. And so time 0, this should be like this. And time n, whatever it happens to be, the line should be here. Does that make sense? Now, does that make sense to everybody else? It's actually, this is a pretty important, I mean, it's well beyond what we're supposed to be talking about today, but it's a pretty important concept because there's a lot of people that are doing research to sort of understand what's going on down here. This is just a measure of activity. It doesn't actually measure what they're doing. This could be one really large organism, or it could be the millions of organisms that we generally think of that are in that soil surface. Okay, so this is just a measure of activity, but it gives us an idea about what's going on in this whole volume of material we call soil. Go.
So, if it means that there is more carbon dioxide at the deeper levels, does it mean biological activity is more down at the shallow regions?
That's actually a good point. Okay, if I have more CO2 down here than up here, does that mean that there's more biological activity down here than up there? No. What it really means is there's more exchange. The exchange of oxygen is faster up there than down here. For that CO2 to exchange and oxygen to replace it, it has to travel 700 centimeters. For it to exchange up there, it only has to travel 100 centimeters. And that's what's happening. And you also have to imagine, with all the organic matter basically being concentrated at the surface, this is actually, this line is actually skewed because, in fact, there's a lot more respiration going on up there than down here. Okay, we good? This is a seasonal. I just sort of, at this point, I think we're beating a dead horse. But here's June. This is basically looking at the growing season, and you're looking at that soil depth, and you're looking at concentrations of CO2. So this is seasonal CO2 content in an alpha soil in Missouri. Okay, and here's depth, and you're basically looking at lower concentrations of CO2 up there than here. But what's really the important story here is as the growing season progresses, you start getting into June and August, where you have a lot of photosynthesis, you have a lot of biomass accumulation, a lot of respiration going on. Okay, and you can look at the CO2 concentration dramatically increase, and it increases all through the profile. Okay. Sooner or later, we're going to start seeing senescence and biological temperatures are going to start coming down. Biological activity is going to be reduced. And so as a result, we start seeing it coming back to fairly similar to what it was in June. Okay, we're looking at what happens at biological activity during the biologically most active time of the year, at least in the northern hemisphere. Does that make sense? This is just sort of a reiterate the question. All right. So I think we made the point at this point, hopefully. We've made the point that saturated soils have little or no air in their pores as the system gets wetter and as respiration happens. Okay, so it's not just the water moving in and driving the oxygen out. It's also the water moving in and the oxygen being driven out and the oxygen being used up for respiration. Okay? Now, saturation can be temporary or in fact could be permanent. A temporary situation is a rainstorm where you come into some sort of permanent, some sort of impermeable barrier, water hits that and then slides sideways. Good example was what you guys saw at the Martins. These are those fragipans. Here's those funnels. You know, the water comes down, hits those fragipans and stalls. Yes, you have some drainage this way, but you see an increase in the water table here, but that water table ultimately is going to slide off and your system will go aerobic again. Another example of this, though, no, this is not another example. This is a different example, a permanent water table, where you're basically looking at the water table coming up and holding there. So this is a permanent. So below this, it's anaerobic. Above this, it's dry, aerobic. Good example of this is up at Mount Pleasant as well. Remember we did that boring? Okay, and we did that boring down at the bottom. Okay, the first soils that we brought up were nice and brown. They had lots of red features, lots of redox features, redoxomorphic features modeling. Okay, but as we went farther and farther down, that red started to disappear. And then you started seeing it just along the root channels, and it became really gray with just red where the root channels were. And that oxygen's not coming from the ground. That oxygen is being pumped down by the plants. Okay? That's a good example of where you're basically at this interface. Above it, you've got oxygen. Below it, that's where you saw those big, bright red models. Yeah, there's a period of time that that's saturated, but it comes back down. Below that, that's where you go into those grays, permanent grays. Okay? You can hold up on that. All right. So if it's about oxygen, what are we talking about? We're talking about respiration. Okay? So when we talk about redox and respiration, we're really talking about basically a biologically mediated reaction. And that's respiration. It's basically how we get ATP. I mean, we're taking oxygen, we're eating food, some sort of organic material with oxygen. We transfer the electron to make CO2 and water, and as a byproduct, or I should say these are the byproducts, and the product for us is making ATP for biological activity. Okay? It's all about getting energy. And so if we're going to start talking about getting energy, we're going to have to talk about the electron tower. We're going to have to talk about where that energy comes from. And I don't know if you guys remember this. This is, let's skip over this one. Have you guys seen something like this lately? You probably all have seen something like that. We're going to talk about that in a moment. But this is basically the electron fall, the electron tower. Okay? When we talk about redox, reduction, oxidation potential, we're really talking about the potential of one substance to accept or donate an electron. And in that acceptance or donation, there is an energy exchange. There is a certain amount of energy that's released that can be captured. Okay? A couple of examples here. This is iron, +2 form, plus water, moving to +3 form, plus proton, and those 2 electrons. Pair that reaction with oxygen and hydrogen, that electron, 2 electrons. This is the complete reaction. I do not expect you guys to memorize this, but what's important is to understand that these are paired reactions. For a substance to donate an electron, it actually has to have something that's going to accept that electron. Okay? They happen at the same time. They're simultaneous. The electron does not exist freely. Okay? We sort of draw it like it's free, it's floating around, but the reality is that this is come from that, and this is going into that. Okay? These reactions occur simultaneously. That's the first thing that we need to remember. The second thing is that this reaction produces electricity, volts. Okay? It's a potential, okay? It's basic, and when we look at this, we're basically looking at we're measuring, this voltage is a measure of that tendency to the tendency of these substances to accept and donate these electrons. Now, the charge numbers that we use is based on a reference state. It's sort of the half reaction. That reference state is the amount of electron energy that you convert from taking basically a H2 and converting into H. Okay? We arbitrarily set that at 0, but that's the default. I mean, don't worry about that. But what is important is more positive the energy, that's the energy, the measure of the redox, EH, the easier it is for that substance to be used as a terminal electron acceptor, i.e., it's going to accept that electron. Okay. Let's take a look at the tower, and hopefully some of this will become a little bit more apparent. Remember, this is a paired reaction, so you're looking at the pairs. Okay, so it doesn't matter which one of these pairs you look at. Let's look at this one, the nitrate-nitrite one. The first in this pair is the oxidizer. This one right here. It is going to be the one that accepts the electron. The second in the pair is going to be the one that donates the electron. Okay? Second in the pair is a reducer, it donates the electron. Now, these guys are not doing it to each other. They're basically doing it to other substances. Okay, so the classic one that we look at is this, because this is what we do. CH2O, some sort of organic molecule, food, plus oxygen. This will go to H2O plus CO2. Right? Actually, I should do that the other way. But this exchange is going to produce a certain amount of energy. Okay. Let's look at that one in particular. CO2 is the acceptor or the donor. We're looking at CO2 up here. Oop, did I skip the right one? Yeah, okay. Oh, the hours are wrong. This red arrow is supposed to go to the food molecule on the top. Sorry. Okay? So, if we take CO2, the pair CO2 and CH2O, CH2O is the food that we're eating, okay? And we respire with oxygen, okay? So the first one is the oxidizer. It accepts the electron. The second one is the reducer. It donates it. So the second one is the food, okay? The CH2O, that is going to donate an electron to the acceptor, the oxygen, O2, right? Okay, so here's my electron. It's going to be transferred to this guy, right? My electron's going to jump. Make sense? In the process, the CH2O is going to be reduced to CO2. The first in the pair is the oxidizer. It's accepting it. Okay, so it's going to be reduced to CO2. So this guy is going to become that. Right? This guy right here, the guy who accepted it, is going to become the water. This is going to become that. And in the process, the amount of energy that was released basically is 0.5 down to 0.82. Or I should say negative, let me say this differently, negative 0.43 to positive 0.82. You add those two up, and you basically get, I actually made it, some rounding error is theirs, but basically you're going to get 1.2 volts of energy. That energy is then applied to making the ATP. Does that make sense? the larger the fall, the more energy you're going to get. So if I started here and I ended here, the delta between them, 40 to 20, is I'm only going to get 0.6. Does that make sense? All right. Here's another reaction using food, but rather than using oxygen as an electron acceptor, system goes anaerobic. We start using iron, right? We talked about this. Use iron, I get less energy per value. Oxygen, I get 1.229. Iron, I get 1.19. Makes sort of sense? Questions? All right. Take a deep breath. We're past the electron tower. Okay? And what I want you guys to look at now is a series of rather important reactions. Now, when you look at something like this, you often think, well, that's the only reaction that's going on. But the reality is there are a lot of reactions going on at the same time in these systems. There's a lot of elements out there. There's a lot of molecules out there that can be used as food. And there's a lot of different elements that can be, or molecules that can be used as electron acceptors. So when I say, you know, we're getting a really good bang for our buck because this is oxygen and food that we're using, okay, it's not to say that the other organisms out there that are not using oxygen aren't getting energy as well. They're happening at the same time. It's just that in the presence of oxygen, you get the largest amount of energy. That's why the oxygen breathers are so successful. We can get more energy for the amount of food that we eat. Okay, so here are some of these elements: carbon, nitrogen, sulfur, iron, magnesium, or manganese. Okay, here's some of the well-known oxidized form. This is basically CH2O. This is basically food. Okay? These are the reduced forms. Okay? Methane, so on. Nitrate versus ammonium or nitrogen gas. Sulfate versus sulfides. Okay, that's just, there's a lot of them. You don't have to memorize them, but I want you to picture in your mind that there's a lot of these reactions going on at the same time. Okay? Here are the half reactions. This is basically these reactions lined up next to each other. I highlighted some of the ones that we see a lot of, but basically here's the amount of energy that you'll get from that paired reaction. Now I want you to see something here. You'll notice that as you go up, you're seeing more and more and more energy released, but you'll note that oxygen's here. So that oxygen reaction with food doesn't actually mean it's the biggest amount of energy that you can get out of it. Okay? There are, in fact, other elements or substances that can accept electrons and donate them that you can get more energy from them. So I'm posed the question then, why is oxygen so important? The answer is way back here. It has to do with abundance. There's a lot of oxygen out there compared to these other elements that can be acceptors or donators. There's a lot more oxygen out there than there is manganese oxide or manganese by itself. Does that make sense? Okay. Now, a couple more slides. What's going on in this slide? Okay, we're looking at oxygen in the soil. Okay, this is basically a percent, so 2 to 18, and we're looking at days that we let that soil dry. We basically take that soil out and we put it on the surface and let it drain out. Okay, now this redox potential basically represents the move of this electron tower from this zone where it's wetter to that zone where it's drier. Okay, so the amount of electron fall is going to increase as the system gets drier. So as the O2 content increases, we have more oxygen to be used as an electron acceptor. And so as a result, the redox, the total redox potential of that soil increases. Now, remember, we've got lots of redox reactions happening. Oxygen is not the only one that is increasing as the system gets drier. What happens to reduced iron when the system goes drier? It goes from Fe plus 2 to what? Fe plus 3. We're basically shifting it from here to here, which moves this reaction, let's go this one, basically from here to here. Does that make sense? So here, how much energy am I getting out of it? But if I start moving it up, I'm getting more energy.
Sorry, what
It's, so if I move from the Fe plus 2 form to an Fe plus 3 form, okay, I'm now making the soil volume have more things that it can accept electrons. And that energy boost is up to here.
But what causes the change?
The cause of the change is the amount of energy that I'm potentially getting out of this system. Because if I have a lot of Fe plus 2s, it's not going to accept any more electrons, right? But if I have Fe plus 3s, I can add electrons to that, and I now have that as an energy source, which in a reduced system I don't have. All right.
So what would I guess what I'm asking is, what are the conditions that would, in the soil, that would make it move from Fe plus 2 to Fe plus 3?
Okay, so the question is, what are the conditions in soil that would make Fe plus 2 move to Fe plus 3? And we can sort of go back to our story about modeling for that one. What happens when the presence of oxygen with Fe plus 2? Go straight to Fe plus 3. Right? So as my system gets drier, yeah, I'm moving more oxygen, so I'm using that as an electron acceptor, but I'm also increasing the amount of Fe plus 3. So if I have an Fe plus 3, this can accept an electron. So I now have more potential than if I had an Fe plus 2. For this to accept an electron, it actually has to go to Fe plus 1. And I don't think that actually exists.
So basically, as the system dries, your Fe plus 2 starts turning into Fe plus 3, which can accept more electrons
Right.
than the Fe plus 2 can.
Right. As your system goes dry, your electron tower moves more negative, goes up, right? Which means the separation between using food as the electron donor and finding some sort of electron acceptor, that drop gets bigger, which means I get more energy out of it. So my EH, my potential, is going to increase as the system dries. It's not just about oxygen, it's about all these other things that are changing as well. Go.
Is food always an electron donor?
In some systems, so the question was, is food always an electron donor? And generally it is, but I think there are a couple of scenarios, and don't quote me on this one, but I think there are actually a couple of scenarios in anaerobic systems where food is actually not necessarily used as, it can in fact not be an electron donor. Because when we think of food as both energy and nutrients, but often food can be, we're just using, for us it's mandatory. But there's a lot of different organisms out there that will use one substance for energy and another substance for nutrients. And I think if you get to a system where the organism is dying and it needs to have food versus something else, it will use energy to get nutrients, or it will use nutrients to get energy. And so they'll play a game between the substances that they're respiring or consuming. But I don't know the anaerobic systems all that well. Okay, we're good with this? Does this make sense? Questions so far? Okay. This is a scenario we're basically looking at a temporal change, a change in time. But we also can look at a change in space. Okay, same time. Basically what you're looking at is a core. This is the aggregate, okay, a large aggregate. Basically this is the center of the aggregate and distance from the aggregate. So here's 0, here's 3, here's 3. We're going towards the edges, okay? And here's distances again. And basically what you're looking at here is the oxygen content. Each one of these isopleth lines is an oxygen content line. Okay? So this core in the center right here is 0% oxygen. And as I get closer to the edge or farther out from the core, I get more and more oxygen. Okay, so what is that going to tell me if I look at this as a graph like this? Where is more of my redox potential? On the edges. Okay, there's more oxygen out here, right? And this is a great example of if this system starts drying on the edges, the water that's in here through capillary action, what's going to happen? It's going to start migrating out to the edges. And if I have a reduced system in here, there's no oxygen in here, okay? Which means all the material that's moving out to the edges is reduced material, right? And if it happens to be iron, moves to the edges, what's going to happen to it? It's going to oxidize and turn red. So I can not only use those patterns of color to give me an idea about redox potential, but it also can tell me a good idea about oxygen content. Where are the organisms that are going to be anaerobic respirers versus aerobic respirers going to be? So right there, I can take a look, and I can say, this is the distribution of my population. Now, granted, this is a temporal thing. You give this enough time, and the oxygen content is going to increase in there. But you can certainly see the behavior of different organisms change as that oxygen content changes. Cool? And it all goes back to this tower. It all goes back to this because they're trying to respire. They're trying to survive. And the amount of energy that you're going to get is based on this electron tower and the conditions that put these combinations together. Okay, questions so far? Feel good about this? No, you don't feel good about this. No. Go.
When you were talking about the soil aggregate and how it respires, you're actually talking about the millions and
The organisms are respiring. The aggregate is not respiring. The organisms are respiring. Sorry.
Just making sure.
Yeah. I really buy into the Gaia hypothesis. That aggregate has now become the blob. All right. Any other questions on that one? We'll take a step back and sort of take a look at the variety of different oxidized forms. Okay. Here's the oxidized form. Here's the reduced form. And basically what you're looking at here is the pair of it. So oxygen is being reduced to water. Okay. We can measure this also to say, well, if I'm going to see this kind of reaction happening, how much enthalpy is actually in the system? How much potential is in the system? Basically, when we see that reaction occurring, we're basically looking at a system that has 0.38 to about 0.32. As the system dries up, you're going to start seeing these other elements being used, or these other compounds basically being used as electron acceptors. They're going to be reduced. And this is the range of EH, or potential, that you're going to be getting off of them. Does that make sense? So what we can do is basically look at these values. We can measure this voltage, and we can basically look at our soils, and we can basically say, if we know what these values are and where they occur, or what level of energy they occur, we can measure the level of energy that's in the soil and tell you, or tell us, how much oxygen, or more importantly, how much water is in the system. If I have an enthalpy, or a potential, between 0.4 and 0.6 volts, I'm probably in a well-drained soil. As that potential goes down 0.3 to 0.35, or 0.25 to negative 0.3, we're moving through a flooded system where oxygen is reduced, or ultimately to a prolonged flooding where the oxygen is basically gone. And you can basically look at the potentials to tell you how much water is in the system, or how much water, how much oxygen is in the system. Does that make sense to people? So I can literally use the potential of the system to tell me what type of reactions I potentially will be seeing, and also tell me how much oxygen is in the system, how wet the system. Forget about the oxygen. How wet the system is. And it's all being driven by respiration. The redox sequence in waterlogged soils, and this will totally make sense to people, but basically we're starting to see oxygen being depleted due to displacement by water and low water solubility and consumption by biological activity. Okay? We get water into the system, that oxygen slows down. It can't exchange as fast. So it's got low solubility. It's moving very slowly. Okay? And the oxygen that's in the system is being consumed by respiration. Okay, that's the first step. The second step is once the soils are depleted of oxygen, anaerobic organisms must use other substances as terminal electron acceptors. That's when we start seeing the shift from this, or I should say from this to these guys, or shift from here to here. As these alternate electron acceptors are being used, the pH starts to rise because most redox reactions start consuming protons. They start consuming those hydrogen ions. Good example of this is the nitrate denitrification, basically taking nitrate and turning it into gas. The NO3 is being used as an electron acceptor, converting it into gas. This is an anaerobic reaction. And in the process, it produces protons, or consumes protons. So as a result, the system basically starts getting higher pH'd. You've basically seen something like this. This is CO2 flux. Okay, we were looking at percentages before. This is actually the flux, how much CO2 is actually escaping from a system. So imagine I got a soil here, and I basically have a sort of a trap here, and I'm measuring how much CO2 is escaping from the soil. Okay? Basically, again, that measurement of respiration. Well, early parts of the season, when it's cool and wet, not a lot of respiration is going on. But once July and later season starts drying, respiration increases, and all of a sudden we see this big boom in CO2 evolution coming off the soil. Basically just a measurement of the respiration. The ecological importance of this, though, really have huge implications. One, systems aerobic, organic matter is going to be decomposed quicker. Make sense? You get more energy for it, faster reactions. Okay? So, OM decomposition is fastest under oxidizing conditions. Okay? As the system goes reduced, because you're not producing CO2, you're producing other byproducts from respiration, toxic byproducts might in fact be produced. And if that's the case, that will slow down the organisms, which will in turn slow down decomposition rates. Yep. That makes sense. I mean, if I start throwing poisons into the system, I start killing off organisms or stalling them, they're not going to be able to do as much decomposition. So by creating the system, making the systems go anaerobic, I'm doing two things. One is I'm reducing the oxygen content, which makes the amount of energy that I'm going to get from decomposition reduced. And two is the system goes anaerobic. The decomposition products are often toxic, or I should say decomposition byproducts are often toxic. And that toxicity then reacts with the organisms that are doing the decomposition, slowing them down even more. Does that make sense? Okay. We also have a sequence of reduction or redox of elements. We have certain nutrients, the iron to the iron, oxidized iron, or Fe+3 to Fe+2, sulfate to sulfite. We also have the toxic production of elements. But we also have the soil colors, which we've been talking about for a while, redox colors. Okay? Those colors are predominantly a result of this, but there's also sulfur and manganese and a number of other different colors in there. We also start producing methane, okay? And methane potentially is a toxic molecule, so back up to this, to other organisms. And we also start seeing a reduction in plant growth. Why? Plants are aerobic, okay? They need to have, their roots need to have oxygen. They're like us. And if those roots don't have oxygen, and they don't have some sort of mechanism to get the oxygen down, they're going to stop respiring. They're going to drown, basically. Make sense?